There it is, the witching hour. Rob 101 comes alive. Better than GMT. We're here every day. Good morning. So we are working on optimization, and we're doing the vector case now. So we got to the basic idea of gradient descent. So we're doing a function that depends on m different variables, but it takes on a scalar value. So it's a real number, and we use it to assign our preference for one solution versus another solution. And here we're looking at minimization. So we let x star equal argmin of all the possible values the function can take on, and we're trying to find that value. The thing we know is that the gradient of the function vanishes at a minimum. And from looking at graphs, and you can also prove it using Gram-Schmidt, though we didn't do that, the transpose of the gradient points in the direction of greatest increase, so the negative of that gets you the direction of steepest descent. And so gradient descent, when you hear somebody talking about algorithms, it's sometimes called steepest descent. You're heading down the mountain in the most steep direction possible. And we did the little topo maps and looking at lines, and yes, you're trying to cross as many lines per distance traveled. So that's the steepest descent. The gradient, it's just first derivatives with respect to individual components of the function, and you arrange those as a row vector. And then you can calculate those individual derivatives with symmetric differences or forward differences or backward, that's not listed. But the most important thing, and we're getting so much mileage out of this, is approximating nonlinear functions at a point as a value at a point, a matrix times a vector. And so in general, this is a Jacobian, but when f takes values in the real numbers, it has a special name called the gradient and this awesome symbol that everybody should want to write down at least once a day, okay? And so this is a 1 by m matrix, so it's a row vector. This is a column vector. You take their product, you get a scalar. Wow. In most programming languages, you get a scalar. In Julia, you get a 1 by 1 matrix, okay? And so gradient descent, the pseudocode would be I start my counter, I set a tolerance to my favorite value, I initialize, and then while the norm of the gradient is bigger than the tolerance and I haven't iterated too many times, I update my current value in the direction of the transpose of the gradient. And with a minus sign and s being a positive number, I get, so that should be selected as well. S positive given. We will descend. And then why it works, we discussed a little bit once again. So we want to choose xk plus 1, that's our choice. You make a different choice, you get a different algorithm. I make a choice, I get an algorithm. We get to choose this. This is fixed, so that means we really get to choose the delta xk, okay? So you can just think about it as choosing the delta xk. And how gradient descent comes about is we trust the linear approximation. So we say it's an equality close enough, and we want the f of xk to be smaller than f of xk, so this is less than or equal to 0. That means we want this product, this row vector times this column vector to give us a negative real number. And the only thing we're counting on really is, okay, so if this is 0, we've already satisfied our local necessary condition to be at a minimum. So we assume it's not 0. And then if we set delta xk is minus s times the transpose of this, then we have a row vector times a column vector, but it's the same vector, the vector times its transpose. This is the norm of the transpose of the gradient squared, because this is the transpose of the transpose. You undo the transpose. So remember our little trick, we had y equals 0 as a vector if and only if y transpose y is equal to 0, which is the sum of the squares of the entries of y equals 0. So it works because this choice for delta x gives you minus s times the norm of the gradient squared. And if s is positive, minus s is negative. And so it works because of linear algebra. Okay, norms of a vector, and you're doing it based upon the linear approximation. And in principle, this is how it works. And this is one of the prettier pictures I found, but I don't know. It doesn't look like it looks like it's rising here to me, so I think that's wishful thinking on the author, but you get the idea, okay? So, and then what we had Wednesday in the chat is, can we view optimization as a root finding problem? And the reason that question comes up is because x star equals arg min, that means the gradient is 0. So what we're looking for are roots of this as a function. That's what we're looking for. So we can do Newton-Raphson. So let's take a look at that. So let's remind ourselves, even though you guys just did a whole bunch of it in the Julia homework, the book does the scalar case first, so you can go through that if you want. So I'm going to do a function, and I'm going to call it something besides f, because we've already taken f to be our cost function. Okay, so I need a different function. And we're looking for roots of this function, so we seek g of x star equals 0, and our algorithm was dg dx dx. Whoops, let me put an xk in there, blah, blah. You don't have to change anything in your notes, really. You just need room. We linearize about our current value. We solve for delta xk, and then we update. Okay, and then d by dg dx at a point x0 is the Jacobian. And it's a matrix. Dot, dot, dot. Okay, let you catch up with this, with your notes, because you're writing much more beautifully than I am, of course. Okay, so G is a vector. It's an M vector. Each of these is an M vector. And we remember that we can calculate the ith one of these, approximately g x0 plus h EI minus GX0 minus HEI over 2 times H. So that's a symmetric difference. So a vector minus a vector is a vector divided by a scalar. That's an M vector. So each column, and so this is an M by M matrix. Newton-Raphson, you just did a bunch of that. Okay, so now what's the issue is, what is our function? I'll write it down again so we don't have to keep coming back, but our function G is the gradient. And so that's what makes it look really complicated. Okay, so for us, so we have X star arg min X in Rm f of X implies the gradient of f evaluated at X star is 0. And so, and that's the same thing as the gradient of f transpose. So this would be a 1 by M vector, and now this is an M by 1 vector. And so the crazy thing is we do root finding on gradient of f transpose. Now this takes M vectors into M vectors. So that's our function G. So we're seeking roots of this guy. That's our function G of X. Kinda works? Kinda works? Nothing in the chat meaning kinda works? Okay, so this is a level up from just gradient descent. So gradient descent, you got that, we're good. Okay, so here's Newton-Raphson. We need the Jacobian of our function G. And then we get minus G, so that'll be minus the gradient transpose, that's easy. The update, that's easy. Solving for this is easy, but what is the Jacobian of the gradient transpose? So that's this awesome thing, okay? So we do the math. What am I on? Yep. So I'll write it like this. We have d by dx of gradient f of xk delta xk equals minus, whoops, there's a transpose there. So that's just brute force substituting in. But it begs the question, what in the world is the Jacobian of the gradient, okay? It looks terrifying, okay? Whoops, transpose. Okay, gradient, row vector, transpose, column vector. Now we've got a whole bunch of functions stacked up. We take its Jacobian, we get an M by M matrix. So this is, everything is all set up to work. Well, this has a name. It's called the Hessian. Bruce. Okay, so this thing here is called the Hessian. And it has a super awesome notation as well to let you know it's a kind of second derivative. So you use the gradient symbol with a square, okay? Does that help us any? Okay, so this is an M by M matrix. So what do we have to work with? How do we compute this? Whoops, wrong one. This, we do symmetric differences, okay? That's how we get the gradient. And then we want to do a Jacobian. We do symmetric differences on these symmetric differences. So you just got to substitute in. So in the book, I do all of the substitutions, okay? But it's not so bad when you're done. And in homework 9 Julia, I just give you the function. It's a double for loop. Look at it. You'll see that it's really not so bad. But it's a matrix. So what is the ij component of this matrix? And because we're using symmetric differences, it has more terms than it would be if you were using forward differences, but it's x plus h times ei, and then it's up to you. You don't have to use, when you're computing this symmetric difference and then when you're doing this one, you can use different sizes of deltas if you want. So that's what this other delta is. It's one small increment, you've got another one, but it's up to you. You can use the same, okay? I often make them the same, but it's a choice. And then it's x plus h ei minus delta ej. Then there's plus a minus term here, f of x minus h times the ith column of the identity matrix, and then plus f of x minus both of them. Okay, and then we got to divide that. Well, you've got 2 delta here and 2h here, or you called it h here and you've got 2h here and you've got 2 delta here, but when you do the product, you get 4h delta. Okay, so that's what the ij term looks like. It's a symmetric difference, but you're doing a symmetric difference onto a symmetric difference. You just need to grind it out yourself for this to make sense, okay? Write down the first derivative in terms of symmetric differences, then write down the derivative of the derivative just using the definition, and these terms pop out. So that's what it is, and it's a double for loop. In Julia. Okay, so, and there's your algorithm, and it performs really, really well. Okay, so I don't know if we should even bother to write it down, but pseudocode. While norm gradient xk. Whether you put a transpose or not, that's up to you. And k is less than k max. We're just going to solve the Jacobian of the gradient transpose, the Hessian, times delta xk equals minus, so this is the fanciest formula we ever get to write down in Rob 101. Transpose, and then xk plus 1 is xk delta xk, and then end our while statement. Here, we're just solving a linear equation, because that's M by M matrix, M by 1 vector, M by 1 vector when we do the transpose. So, okay, so you write your little function that produces the Hessian and the gradient, and in Julia homework 9, we're just giving them to you. And so you call that, bingo, whoops. Here's the Hessian, M by M matrix. Here's the gradient, you transpose it. I guess I want a step size in here, don't I? Minus S, there we go. Okay, and then Bruce mentioned that when he was doing the fitting work, hey, what happened to it? Okay, so Bruce was trying to align the LiDAR sensor and the RealSense camera, and what he was trying to get would be the transformation that takes you from the point of view of the camera and the point of view of the LiDAR and lines them up. And so this is what you want them to do. This is often what you start when you just mount them onto the thing and you use your CAD file to have an approximate that I know it's 11 centimeters here, but I don't know exactly where the origin of the camera is. I don't know exactly where the origin of the LiDAR is, so my translation in the X might be off, and then the mount might not be perfect, and so this is a little bit like this, and the LiDAR is a little bit like this. You need the rotation matrix that lines them up. So that's what he was trying to do. I think he was intimidated by you. You saw how fast he was speaking. Did anybody parse him out? Okay. So usually you guys watch me on 1.5x on the video. I recommend Bruce at 0.3, okay? But if you go through it, you'll see that it's an amazing optimization problem. It's a nonlinear least squares, because when you map the LiDAR points to the camera, the mapping from the camera to the 2D image of the camera plane, that is a nonlinear function. You end up dividing by distance. That's a depth. And that's what gives you focal regions of a camera. That's nonlinear. But then once you have your points down on the camera frame, you're doing least squares to line them up. And so that's the problem he set up, and he solved it with gradient. And it took something like 3,000 iterations, and then with Hessian root finding, it solved itself in 14 iterations. Okay, so even though you're doing the extra work for the Jacobian of the gradient to get the Hessian, right? That's extra work to calculate this matrix versus doing gradient descent over here. Then you've got still a much higher performing algorithm, and it got it in 14 iterations versus 2,000. So root finding, and then you guys will do that in Rob 101, homework 9, Julia, the very last one, and just a couple problems there. Cool. Questions on the second order method? We say it's a second order method because the gradient, that's a first derivative. We do gradient descent. We call that a first order method. And then when we do root finding, we're doing the Jacobian of the gradient. So it's a second derivative. We get this awesome symbol, the Hessian, and that's a second order method because we're doing a second derivative. But we can still do them numerically. You can speed up your algorithms by doing them analytically with SymPy. Is SymPy working for homework 9 or not? Do you know? It's working? Okay, you get to play with symbolic derivatives in homework 9. So Wami uses them in Mathematica, I think is what you're using. And you've also done them in the symbolic toolbox of MATLAB, right? So there's lots of packages available. Okay. Well, if you're good with that, I just want to make a few comments then. Global versus local. Okay, so bingo, bingo, whoops, bingo. Insert, image, file. Do something awesome. Yeah. Okay. Remember these two cost functions? Those were the first two we looked at for the scalar case. This one has, whoops. This one has local minima. Looks like a global if everything keeps going out afterwards. It has a local max. Whereas this one, you know, that looks like a quadratic, it's gorgeous. There's only a single minimum. So we kind of like, wow, can we find cost functions that look like this one? That would be like super fantastic. And if we could avoid that, that would be wonderful because then all of our optimization problems would have unique answers, and it's probably much easier to converge when you're always pointing downwards and you're not trying to go over bumps and do multi-start. So there's a property here called convexity. And as a geometric construct, a function is convex if I take any 2 points in the graph of the function and I connect them with a line, the line lies above the function. So you see here, here's a line, but the function is above it there, but it's below it here, so it's not convex. So this is the geometric construct. I give the analytic version in the book because that's how you can translate the notion to functions that depend upon 200 variables or something. And so there's a whole range, there's a whole new area now that's super hot. Called Convex Optimization. And it's when you can prove your function is convex, you get super fast convergence, you get uniqueness, you get a whole bunch of wonderful, wonderful, wonderful properties. My hope is that Professor Ram Vasudevan will have a course at the 3rd year level within 2 years from now. So it'll be ready when you guys are. So I would look for it, okay? wonderfully useful. It's something that's only available to graduate students now, this type of material. So we're going to try to get that available as an optional robotics course. I don't know, Wami, would you guys like to get started?
Sure. I think they were on their way. It's not already here, but they're in.
Well, okay, I can do, why don't you Slack them and say, hey, Jesse's ready for you.
Sure.
Okay, and I'll be the warm-up act then. The main band is about to take the set, and the warm-up act is going to go back and say, well, just the fact that he's associated with this group is going to raise his stature. So this is project 3, the last project, this segue project. Okay, so the whole idea, these things look crazily unstable, right? I mean, there's no reason that thing should be staying up. So, because it's a pendulum, but it's inverted, okay? This, nicely, we understand why the pendulum stays down, but every time we try to make the pendulum go like this, it goes like this, and that would hurt. Okay, so these things are inverted pendula. How is it that you keep those things upright? Now, they've been around for a long time, and you're probably thinking, wow, come on, everybody has them, and we have all sorts of miniature skateboards that are powered, and 1 wheel, and 2 wheels, and all this kind of stuff. But how you make them work is totally amazing. Fantastic, see, I just had to go into the warm-up act, and then the band got here. Yep. Okay, you guys, you need to take one of these wipes. And Eva, I'm going to ask you to clean the, yeah, take one. Wami's already done this. Eva, you take one. Clean this microphone cord for Eva. Okay. She should do it herself. But you're going to have you use the mic, you and Wami, Grant, but, yep. Yep. Okay, so they're going to go through and talk to you about how F equals MA gives you models. But the main thing we're going to lead you to is that we can take physics and convert it into, when we do linear approximation, models that look like this. This is like the position, the velocity, the steering angle, the turning rate of a car, for example, at time k. This is those values at the next time, and these are the things that you get to manipulate. You get to control those. You get to control the throttle, you get to control the steering wheel. So, you're all set? Yep. You're ready for HDMI? Yes. Going live with Eva Mungai, Grant Gibson, and Wami Onyubo, and I can't get the last part. You're going to help when we get there. So,
you can also go by the Waminator.
Yeah. Okay. The people online cannot hear.
Stays on as the eventer. This is match point for Ape Escape.
Hey, Grant, why don't you just start talking?
Okay. Where the camera is right
yep.
there.
So
Okay.
It's here is where the camera view is. You need to clip this on just like I've got it here. Yeah. Oh, you got it. You plug that into here with the black button facing forward, all the way in. Yep. And then I'll turn it off. If you'll speak, and we'll let you know if they can hear you.
All right, can you guys hear me?
I think that came over the speakers. Put this in your pocket.
All right,
Okay.
let's, what happened to my PowerPoint presentation? 1 second, y'all. It disappeared.
Start talking, Greg.
Okay, cool. So, yeah, so kind of as Professor Grizzle talked a little bit, we're going to overview the optimization, control with optimization project that you guys will be completing over the next couple weeks. We have some cool kind of real world examples to show to start off with that kind of inspire what happens at a low level and kind of simpler models. And so we'll kind of show some examples, cool examples, talk about a simpler thing you guys will try and implement.
I see your lovely family, which
Yeah.
is fantastic. Okay, let's all go here. We all want to go.
All right, that,
There we go.
There we go. Okay.
Much less interesting.
let me
Okay, go for
get
it.
this on now. All right, cool. So yeah, like Grant was saying, today we're, oh, that's the camera?
Yeah.
Over there, cool. Today we're going to be talking about model predictive control. And so just to give a sort of motivation as to what this is and why we use it, well, we actually all use model predictive control in everyday life. So an example that we can think of is, if I can get this video to play. Cool. So this is competitive tag, right? And I mean, we've all played tag when we were little, right? And so what happens in tag is that, you know, you kind of try to see where your opponent is going, and then you try to make moves based off of where you think they're going to be, right? And so this is what model predictive control really is. What it does is that it makes moves based off of what you think is going to happen in the future. And then as things change, you modify your moves, right? So you can imagine in tag, right, if you just kept doing the same strategy, right, and your opponent caught up to your strategy. Well, if you don't change, they're going to tag you, and then you're out of the game. So this is what model predictive control does. And this is just a really, really cool example of adults playing competitive tag, which I think is pretty dope. I mean, that takes a lot of skills to do. And so, I mean, to kind of give y'all an idea as to what this is and how exactly we can apply it, we're going to talk about a simple example, so a self-driving car.
Right, so Eva kind of talked about how we as humans, you know, we have a brain, we have muscles, how we kind of go about doing our version of model predictive control. But how would we kind of apply this to a robot or some type of system that we can control? So this is one of the first examples that you guys will encounter on the project to kind of give you guys some insight into how this works. So we kind of simplify everything, and we just imagine you're in a self-driving car that can only go in a straight line. We have a state of our car, which represents things that we either want to know about the system or things that we have learned about the system. So in this case for a car, we might know the position of our car and the velocity of our car. And after we have that kind of state information, we might say, oh, we want to go to some desired position. So, you know, you're on a bus, you want to go to the next bus stop, that is some desired goal. And there's kind of two ways to think about getting that car to the next location. So you might have control over the throttle, like you're driving a car. So you might have to think about what type of forces do I need to apply to a throttle in order to get me from point A to point B. And so we kind of go into more details in the project. You'll kind of see Professor Grizzle highlighted some of the finite difference equations that are used to explain this. But more at a high level, we can kind of think about getting a car from point A to point B with two methods, open loop control or closed loop control. And so Professor Grizzle termed the coin blindfolded control for open loop. So imagine you're in a car and you see some desired goal position that you want to get to. You take off your blindfold and you see where you want to go. And you kind of calculate where you, like, you know, how much should I press the throttle? How much should I let go? A computer obviously can do this a little bit better. And then you put the blindfold back on and you just run the system for, you know, however long you want. That's all fine and good unless you have, you know, anything in the environment that changes. So, you know, mud could get on the road, the incline could be steep. These things are going to throw off that initial calculation that you made. And so that kind of leads you into what's called closed loop control or eyes wide open control, where, you know, if you always have your eyes on the environment, you can always kind of recalculate the kind of throttle force that you want to apply to a car in order to get it from point A to point B. And so this is kind of just a high level image, and you'll kind of be able to explore this in the project a little bit more.
Yep, and just so y'all can see that this is actually something that's utilized in real life, here is an example of a car, self-driving car over here that's driving using model predictive control. As you can see, what we're looking at over here is that it plans its trajectories ahead, right? And by doing this, it's able to actually navigate all these various paths. So again, we can go back to the competitive tag example, right? Where kind of like what Grant was saying with blindfolded, right? You can imagine playing tag while you're blindfolded. That's not great, right? I mean, you're gonna run into a wall, it's not gonna work out, right? And so this is what model predictive control allows us to do, and this is what this eyes wide open control allows us to do. You see where you're going, you make your adjustment, you see what's going on, and yeah. So it's actually used in real world. So y'all are not wasting your time. That's good, right?
It's always nice to not waste your time. With that being said, let us segue into the main part of this project. I have to use the pun at least once. So yeah, go ahead and go to the next slide. So we have here a video right here. And the link to this video is on the document that you'll be, I guess, perusing. So I encourage you to listen to this with the sound on so you can understand like how segues work. That's what the narrator is going over. But the general gist is that if you are tilting forward on a segue, the sensors in the segue are going to sense that forward tilt, and the controller is going to tell the segue to move forward. Similarly, if you tilt backward, the sensors are going to notice that backward tilt. And then the controllers are going to tell the segue to move backwards. And yeah, that's just basically the general overview of like how a segue works. In terms of, how do I do this? Okay, thanks. So we have laid out this like diagram along the top of the screen here that kind of like goes over like the logic flow of like how from getting the information to like acting on the information. So first you have the sensors, right? It senses if you're tilting forward or you're tilting backwards. To get that, it also gets that position and velocity information. It sends that information to the microprocessor, and this is what your controller is. And that controller is going to take that information and it's going to generate some sort of output, which is going to give to the actuator, which is your motor, the thing that's turning the wheels of the Segway. And then, yeah, so the motor's going to turn the wheels of the Segway, which, influences the physical components of the system, right? So this is your, I guess, things including like the tilt of the Segway itself. And of course, the angle difference is going to be picked up by the sensors, and that whole loop loops all over again. And you go all the way through that process until you get to your goal state. So the objective of your project here is to essentially, we're going to give you an initial state values. So meaning like just the initial positions of your Segway, the position and initial velocity. And then we're going to tell you to get to some sort of goal state. So by looping through this logic loop, you can basically design your controller such that you get to that desired goal state. And so you're going to be using basically all the information that you learned in the examples that we tell you in the self-driving car example. It goes through all this logic. It's just you're just now applying it to a different system. But that's about the general overview of this project. I guess we can take questions, maybe?
Yeah, take questions. Let's get the chat up. Let's see.
I slid it.
No. Okay. Oops, sorry. No. Not a touch screen. Yeah. Let's see. Yeah. Hey, you guys have questions out there? And for Eva, Grant, and Wami, thank you. We had Bruce on Wednesday, and he was intimidated by this group. And he gave all the words that you guys just gave, but he gave them in like 5 minutes. Okay?
Oh, fun.
Well,
these guys are not intimidated by anybody. This group of people right here.
Oh no,
absolutely
I'm
not.
great for the puns and all that.
I mean, I guess does the general idea of model predictive control make sense, and why this is something that we actually want to use. I'm seeing nods in the audience. I'm guessing people in the chat. Right?
Yeah, and we have a question in the chat. So someone asked, so is the open loop and closed loop control kind of like a feed forward and feedback term? And they're already using those buzzwords. Let's hear.
The answer is yes.
Yeah, the answer is yes. I don't know if Grant is a better explainer of this. I tend to ramble, so.
Yeah, so exactly. So it's open loop and closed loop. Yeah, so the open loop has no type of feed forward or feedback term. You're simply we kind of have here plant, but that's like a fancy. That's kind of what all the. If you want to look cool and talk to controls people, you say, I'm running something through my plant. I don't really know where the term came from, but yeah. So with open loop control. There's no feedback term. You can see there's no kind of information of where you currently are. You kind of just apply your torques and you hope for the best. But you're exactly correct. With closed loop control and this model predictive control, you always have this loop back. So after we pass our input through the plant, we actually figure out, okay, I applied a throttle force or something. Okay, what is my new position and velocity? So yeah, that's exactly what's happening here. And there's tons of different ways to do feedback control. This is just one of the methods.
And I just want to point out this tracking error over here. Again, that's you making adjustments based off of what you've seen. And so that's what makes this feedback loop very, very powerful. Whereas in the other one, I mean, you get absolutely no feedback at all. You can think about it as if you were throwing darts and you have absolutely no idea where your darts are landing, right? So if you're blindfolded, you're gonna keep throwing the darts outside the circle, right? But as soon as you can get that feedback, you can be like, oh, let me adjust it over here. Or even when you're shooting a basketball, right? It's like, oh, I hit the rim that time. Let me move a little bit to the left, a little bit to the right. So yeah.
Cool.
Other questions?
No. I will say this type of course where you go through learning optimizations, you can, what we've kind of found, like I think when I was an undergrad, I didn't realize this, but really anything you work on, any system, the sciences, engineering, even some humanities, like optimization can really be used as a baseline for solving a lot of your problems. So this is just one example of how we're going to be using an optimization framework to solve a specific controls problem, but you could think about using this type of framework to do many other things. Cool.
Okay, I'll add a few extra comments while we take the box back, Eva.
Oh.
Unplug. That'll help. Once you leave that there. Okay, so just a little bit more about segue. Why is it that when you lean forward, you accelerate? Okay, why is it if you lean forward, you accelerate? So let's, yeah. So I know the camera is very far away and it's getting ready to turn off, etc. But the thing you need to think about is the wheels are in the cart that's under your feet. If you're leaning forward, the only way to prevent you from doing a face plant is if the cart moves under you to try to catch up with you. And if it accelerates fast enough, it will invert the pendulum and stand it up. That's how it works, okay? So it has to constantly measure the angle of the pendulum and then move the position of the cart to keep it at a given angle. So if you're leaning forward, you're accelerating because the cart is continually accelerating, trying to push it forward, but you're leaning forward on the handle until you reach the max speed of, say, 15 miles per hour or whatever the Segway has. Okay? Now, the other thing is, suppose you're at equilibrium and you want to displace the Segway by like 10 centimeters. 4 inches, okay? The cart just can't start driving in that direction because then the pendulum goes backwards. You guys understand that, right? You have a pendulum and the cart goes forward, the pendulum goes backwards. So it has to first back up, lean the pendulum over, drive under it, and stand it back up. That is hard, okay? So this is where the model predictive control comes in. It has a model of how the pendulum interacts with the cart. That's the Segway model. It knows that. You want to get to here, you're going to use least squares control, minimum energy control, to take you from a given position to the goal position. And the model says, if I apply this sequence of controls, what is the effect on the displacement of the pendulum? So model predictive control is predicting the future using your model based upon hypothetical control actions. You then optimize over all possible controls that'll get me from point A to point B. And that's how model predictive control works. And it's model predictive to see the future, but you're going to compute a whole sequence, apply one of those controls, see what it really did, recompute your control, and keep going. So it's a little bit weird. It's all explained in the handout, and you're going to have a blast, okay? That's all I can say. So Eva, Grant, and Wami, thank you very much for coming and coming up with this spectacular project for Rob 101. So you've got almost a month to do it. We wanted to get it out there because we know everybody's busy at the end of the term. So thank you for your attention, and thank you guys for building this wonderful project.